So my name is Ranjit, and my co-authors are Gaurav Jaswal, Aditya Nigam, Arnab Bhavsar, Sudhir K. Pathak, and Atish Kumar. My paper title is HLGSNet, that is Hierarchical and Lightweight Graph Siamese Network with Triplet Laws for fMRI-based classification of ADHD. So let us start with MRI. So this is the MRI imaging. So here if you see we have theta slash scanner. Inside this scanner we have patient, and then signals are coming from this scanner. So here this is K space. So this is 2D matrix between phase and frequency. And then we are applying inverse Fourier transform so that we are getting final output image. So in MRI we have mainly two types of imaging. First one is T1 imaging and the second one is T2 imaging. Now come to the functional MRI. So how the functional MRI is different from MRI. So this is the MRI. So here this is the one 3D volume. So this is single volumetric data to study the brain structure. So here we have high spatial resolution. But in fMRI we have a series of 3D volume, that is 4D data, but each volume is having a low spatial resolution. So but at the same time it has a high temporal resolution. So this is a volumetric time series to study the brain function over time. Now come to the fMRI pipeline. So this is overall pipeline. So we have fMRI data, then we have several pre-processing steps. So we have skull removing, slice time correction, and so on. Then we have region along with the time series extraction. So this is here we parcelate brain into different regions. Then for each region we have average signal, and then based on that signal we are constructing this connectivity matrix. So this is the visualization of the connectivity matrix among all the regions, and then this connectivity matrix would be used for different applications. So these are the several applications for this connectivity matrix. Now come to the problem definition. So we have considered ADHD data set for our problem. So this is one of the most severe neurodevelopment diseases impacting 5 to 10% young children between the age of 6 and 12. And for this disease, we don't have any specific diagnostic approach. So the diagnosis is totally depends on finding typically over months by doctors or parents. So in this way, if you see, this is a very time-consuming process and costly also. So now come to the problem statement. So we propose an end-to-end CNN architecture that is hierarchical and lightweight graph Siamese network for classification of neurological disorder, that is ADHD, from fMRI data. So this is the input for our network. So here we are providing two things, that is adjacency matrix and then feature matrix. And this is the output level, that is 0 or 1. 0 is for normal, 1 is for patient. Now come to the related work. So this is the related work. So here in this first, the authors have proposed an end-to-end deep learning model to learn the network representation for classification of ADHD using fMRI data. So authors have performed experiments in 3 steps, including feature extraction followed by similarity and classification. So in this second, the novel FCNet is proposed to obtain the inherent features of raw time series signal by getting function connectivity directly from raw fMRI time series signals. Now come to the proposed framework. So the first step in the proposed framework is to get the graph. So a graph is defined by G, that is V, E. So V and E are set of vertices and edges. So in our case, what we have done, we have parcellated brain into 116 regions by using the automated anatomical labeling atlas, and where each region represents one node for the graph. So now for graph reconstruction, first we compute the average of the signals from all the voxels of each region. Moreover, the length of each signal is 171, since we have 171 time instant. So in this way, any brain V can be represented as a signal f of size 116 into 171. And if you find the correlation among all the regions, so that correlation matrix C will be obtained. Will be obtained is of size 116 into 116, and then by putting some threshold we can get the adjacency matrix A. So this is the visualization of absolute difference between mean correlation of normal and patient, and here also we are putting some threshold on absolute difference. Now come to the proposed framework. So this is GCNN framework. So here we have input, that is we are providing A matrix, that is adjacency matrix, and the feature matrix. And this is the first convolution layer. So this is Chebyshev spectral graph convolution layer. So here we have spectral filters represented by kth order polynomials. So here we are taking k equal to 25. So after this layer, we are getting feature matrix that is of size 116 into 256. So we are going from 171 features to 256 features, but adjacency matrix will be remain same. Now this is the pooling with embedding layer. So what it will do, it will mapping the mapping the nodes to a set of cluster, which then form the quotient input for the next GNN layer. So if you see here, so we are going from 116 nodes to the 92 nodes. After that, we are applying one more convolution, that is Chebyshev layer. Then we are pooling pooling with embedding layer. So finally here we are getting a matrix that is of size 73 into 73, and feature matrix that is of size 73 into 256. And then after that, we have a global averaging pooling layer that will average the value across the nodes. So that finally we'll get the 256 dimensional vector. And at last, we are applying a fully connected layer, so that we will get the 64 dimensional feature vector. Now, so we have trained our network in Siamese base. So if you see here, we are providing three things, that is anchor, positive, and negative. The class of anchor and positive are same, but the class of anchor and negative are different. So we are providing this to the three shared networks. So this is graph CN that I already have discussed before, and each shared network will give one embedding that is of size 64, and then finally we're applying triplet loss on this. So this is the triplet loss. So this is here this is Euclidean distance between anchor and positive, and here this is the difference between anchor and negative. So our goal, and plus we have some alpha margin also. So our goal is to minimize this distance, but at the same time we have to maximize this distance. Now come to the dataset specification. So we have two datasets to validate our approach, which had also utilized in ADHD 200 global competition. So each data has both training and testing data separately. So these and each data already has preprocessed. So these are some standard step for preprocessing. Now come to the training and testing strategy. So the proposed HLGSNet has been trained over only 270 subjects, where NI containing 48 subjects, and NY containing 200 to 22 subjects of both normal and patient. So for testing, NI containing 25 subjects, in which 14 and 11 belong to normal and patient respectively. For testing, NYU containing for 12 subjects for normal and 29 subjects for patient. Since we know that we have less number of data, so if you have less number of data, it may have overfitting problem. So for reducing the overfitting problem, we train our network based on triplet. So what we have done, we have generated 1 lakh triplet from 270 subjects. Now come to the performance parameters. So these are the performance parameters. Here we have these three performance parameters. The first one is sensitivity, that is true divided by true positive plus false negative. Then specificity, that is true negative divided true negative plus false positive. Then we have accuracy. Now this is the result. So we for NI we are getting 68% accuracy, but at the same time we have sensitivity is 72.73%, and specificity is 64.29%. For NY we are getting better accuracy than NI, but in the case of sensitivity, this is lesser than NI. But we know that sensitivity is a very crucial thing, because it tells that how many actual patients are correctly classified as a patient. So this is a very crucial thing. Now come to the comparative analysis. So in comparative analysis, so if you see here, we have this is proposed framework. So we are getting accuracy that is 68%, that is better than deep fMRI, slightly better than deep fMRI. But if you go for sensitivity, we are getting approx 10% more than this deep fMRI, which is and we know that this is very, very crucial thing. So in the case of NYU, also we are getting accuracy 68.29%. This is lesser than this deep fMRI, but sensitivity is better than the deep fMRI. So now come to the conclusion. So we present an end-to-end hierarchical Siamese classification network for classification of ADHD and control subject. Experimental finding of our methodology indicates encouraging success on ADHD 200 data set. Thank you.